think about me?
Only good things.
Okay, I take your word. So I'm here today to talk about Postgres system architecture. To begin with the definition of software architecture. This is from international organization. It's a fundamental organization of the system, blah, blah, blah. I'm not going to go into details of that, but there are many definitions of what exactly it means. If you Google for software or Postgres architecture, you will get a lot of pretty pictures and so forth. I don't actually have any diagrams in this presentation. I was going to, but just somehow ended up not having any. The point is that software architecture definition it's not a single diagram, because there's always multiple things you want to look at. Like, I'm going to cover what processes Postgres has, and how does the memory management work, and what's in shared memory. But you could also take a look at how the source code is organized, and or how does the client and the server communicate, and so forth. So there's a lot of different viewpoints you could take. In a nutshell, software architecture is just it's the same thing as software design, just a higher level. And it is just a software architect that decides which things are important. And this presentation is based on my opinions, and I just picked a few things that I find important that I usually work on. I'm sure there are a lot of other things that are important to different people, but this is just based on some things I haven't picked. If you have any questions at any point, just feel free to raise your hand and interrupt. We will also have some time at the end for questions. So software architecture is all about trying to achieve some non-functional requirements. And what we mean by non-functional requirements is things like data integrity. It's very important for Postgres that you don't lose your data. We care a lot about that. So we make some decisions based on that. How do you make it reliable so you don't lose your data? And there's things like performance. You probably want it to perform well. You want it to scale well so that if you have 100 cores on the server, you can make use of all of that. In Postgres, we also care about scaling down. If you take the stock Postgres installation, the defaults in your config file are tuned for like a tiny little server. And that's by design also. Postgres, you can run Postgres on tiny machines. I have a Raspberry Pi running in my bookshelf at home. It's a build farm member called Chipmunk. If you go to the build farm webpage, that's running without the box. It's just a plain board with an Ethernet connection on it. And it runs Postgres. Every night it does a build. And it works fine. I used to run it on 256 megs. That was a little bit tight, but it ran. Now I've upgraded to 512 megabytes RAM, and it works perfectly. So scalability, we care about scaling up, but we also care about scaling down. Reliability, in this case, could mean a lot of things. I mean, if something goes wrong, the system keeps running, as far as it's safe to do so without, again, corrupting your data. We care about interoperability. We follow the SQL standard. We try to be interoperable between versions, for example. We also care a lot about portability. You can run Postgres on all kinds of strange hardware. I think we used to have a PlayStation in the build farm. We don't anymore. I don't know what happened to that. But you can run it on Raspberry Pi. You can run it on all kinds of strange architectures. We have HP UX box running there, I think. And we're just having discussions on the list right now about re-architecting some low-level spin locks and atomic operations, and we're having discussions like, do we still need to support Spark version 8 that was released in 1998? I think most people are now agreeing that we don't, but we're having even a serious discussion of whether we still need to support these things. So Postgres is very portable to all kinds of servers, and we also support Windows, which is one of the that's one of the more difficult parts. Porting to a different CPU architecture is simple. And we care highly about extensibility. Postgres has, you can extend it in so many ways. You can build your own data types. You can obviously build your own functions. But you can also write your functions in all kinds of different languages, Perl, Python. And if you invent a new programming language, you can create a PL handler so that you can write your functions in that new language. I hope someone will write PL languages for Go and whatnot. There's all kinds bunch of new interesting languages coming up. I don't think anyone has done that yet, but that would be completely doable. We care about maintainability. We reject a lot of patches that improve performance, for example, if it makes the code messier, or if it improves some scalability or whatnot, but it makes the code more difficult to understand. We care about that. We reject patches on the grounds that it's difficult to read, and we care about code comments. The Postgres source tree is very nice to read. So these are kind of the values of the community on, whether a patch is accepted or not, or what do we usually work on. It's kind of these kind of things. I'm sure I left out something like Postgres gave a whole presentation on security. I didn't think of that, but that's one of those things that you have to design it into the architecture that you can then implement all these features that make it secure or whatnot. So just one example. Postgres is very extensible. You can create your own operators like plus, minus, divided by, or you can invent your whole new names for them. And you can define what data types it works on, and then you implement it by using a function. And you use this for even all of the built-in types. So, for example, if you look at the implementation of the less than operator for plain integers, Postgres, every time you use the less than operator, it goes and calls this function. It's built in into the system. It's not an extension or anything, but it goes through all the same kind of code paths that you would if it was an extension. So all the built-in types are exactly the same as kind of data types you can write your own. There are no exceptions to, or very few exceptions to how we handle built-in data types, or we handle your own data types that we plug in. And that makes it very extensible. That's basically what makes things like PostGIS possible, where you have build your own data types and you can represent points or graphs or whatever, and the system will work fine with them. You just have to define the behavior. I mean, what does it mean? What kind of operator does it make sense for points? Is it within a box or outside a box? While for an integer you have less than, greater than, and so forth. It's up to you to decide what these things mean. And Postgres doesn't care. It will just call your functions based on the rules you give it. What do these mean? Of course, when you're hacking on Postgres, it means that you can't assume anything at all about the data types. You always have to go through these functions. For example, there is no special case code for sorting integers. If you have a table with an ID, integer ID column, it's actually pretty slow compared to many other databases because we don't have anything special for them. It goes through the same kind of hoops that you would if it was a point or if it was a long blob of text. We use the exact same code paths to deal with integers. Of course, integers are always small and they're fixed size, so we know about that and we take advantage of that. But you can write your own fixed size data types and you will get the same benefits. So it's a trade-off. It makes it very extensible and it makes it possible to write PostGIS and many other extensions that use these things. But it also means that building data types can be as slow as extensions in a way. There are no fast paths for them. That was kind of just an introduction on what these non-functional requirements mean. So I'm going to do next. I'm going to go through some of the processes that Postgres has. So if you probably know, Postgres consists of multiple processes, and they communicate with each other, and they communicate with the client. So when you start up Postgres, the first thing that it launches is the postmaster process. That's as the name says, it's the master of all these other different processes. And for every connection to the system, the postmaster launches a new backend process. So there's always one process in the server for every connection. When you connect to the server, it launches a new process for that connection. And that makes it very scalable in the sense that if you have 100 connections, you will end up with 100 processes in the server, and each one of them can typically take advantage of one CPU or core. So that makes it pretty scalable. Then we have a lot of auxiliary processes or additional processes that are not attached to any connection. We have all the stuff related to auto vacuum. Whenever auto vacuum runs, it launches a new process to handle that. Then we have a few stuff like background writer. Well, there's a lot of stuff there. As a new feature in, I think it was 9.3, we have the ability, you can write your own background worker processes. If you want to extend Postgres so that there's a new process that just does stuff in the background. Maybe if you want to write a scale level like cron, or if you're building your own replication system that needs to have something running in the server all the time, you should write it as a custom background worker so that it works like any other process in the system. So when you launch Postgres, you will see these processes. In this case, you can see the checkpointer, background writer, and so forth. You can, the regular Unix processes, you can see how much CPU time you're spending, or which process is busy, and so forth. So Postmaster. So that's the master of all the processes. It doesn't do much. It does very little. It's just whenever a new connection comes in, it launches a new backend process to handle that. And it also handles the death of the child processes. So whenever you disconnect, Postmaster will notice that, hey, this backend process died, and it will check, well, did it clean up after itself? And if the backend process did not clean up nicely, if it crashed, then the Postmaster will realize, oh, oops, one of these backend processes crashed, and we don't know what it's doing. It might have been in the middle of modifying the page or doing something dangerous. So it will shut down the whole system so that you don't lose your data or you don't corrupt your data. So that's very important for data integrity, that you have this Postmaster process that will shut down the system relatively safely if something goes wrong. So for the Postmaster process itself, it's very important that it's reliable, because we rely on that to be there. If something else goes wrong, the Postmaster is responsible for killing everyone else and shutting down the system safely. So it's very important that the Postmaster never dies itself. If it will, then the backend processes will notice that, and they will kill themselves eventually. But the better way to do it is to have the Postmaster realize that something went wrong and shut down the system safely. That is why the Postmaster process, it's attached to the shared memory, technically, but it never does anything interesting with the shared memory. It just doesn't touch shared memory. Again, the reason for that is reliability, because if the Postmaster process went around the shared memory doing stuff, it would be more likely that a bug, makes the Postmaster crash, and we don't want that to happen. Or also, there's no locking between Postmaster and the other processes. Again, for the same reason that it could happen that one of the backends crash or hang, and then we would have the Postmaster blocking on that, and it would also hang. We don't want that to happen. So the Postmaster only looks at the processes and doesn't communicate much with the other processes. And it's very small. It uses very little memory, and it's very little code. The normal backend processes, there's one per connection. The backend processes themselves, they communicate using shared memory with other processes. So there's a large sized area of shared memory that I'm going to go into more details of that. There's a large chunk of shared memory that the backend processes use to communicate with each other. But the basic life cycle of the backend process is that the Postmaster launches it when you connect. The backend will authenticate the client, and after that, after it has done the basic authentication, like where did this connection come from? Is there a role for this in the pghpa.conf, and does the basic stuff. It will then attach to the database that the client wanted to connect to. It's part of the starter packet that the client sends. And after it's attached to the database and verified that you're allowed to connect to that database, you can then start to execute queries. And we'll just go into a loop where query comes in from the client, it executes it, sends the result back, and then the next query sends the result back. Until it's time to disconnect, or the client disconnects, or if something goes wrong in the backend, it will shut itself down. It will detach from shared memory, so that the postmaster sees that it was a clean shutdown, and then it will exit. And when you launch a new connection, then your backend will be spawned. Then there are a few special processes. When you do crash recovery, if your system crashes or you pull the power plug, when you start it up again, the postmaster will first start up what we call a startup process. It's kind of similar to a normal backend process, but it only runs once when you start up the system. And what it will do is it will read the control file that's in the data directory, which contains some basic information like which version is this data directory, so that if you try to launch it against the wrong version, it will complain. And it will read basic stuff like, well, what is the locale and encoding, stuff like that. But more importantly, it contains the pointer to the latest checkpoint. And it will determine if you need to do while recovery, if you need to read the logs. And then it will go ahead and read the logs and replay all the while recovery it needs to. And so that's the responsibility of the startup process. It doesn't do much else. Once it's done with the startup, with the while recovery, the startup process will exit. And the postmaster notices that, okay, the startup process died. It will check the return code, and if it was successful, then it will launch the rest of the system. It will open and start to listen to connections. So the startup process is responsible for bringing the system up to the point that it's safe for the clients to connect. If you run streaming replication, or any kind of replication, you will see the startup process running all the time because you're continuously in recovery. You keep applying the logs as they arrive. So in that case, the startup process will be there until you promote the server. At that point, the startup process will exit and let the system open up for write connections. Then we have a few more processes. You can see the background writer and the log writer. These are kind of not that important. They're not attached to any particular database. The only reason these exist is performance. The background writer scans the buffer pool and writes out the dirty pages, and the purpose of that is that whenever a backend needs to read in something, otherwise the buffer pool would be just full of dirty pages, and now the backend has to write a dirty page first to make a room for a new one. So the background writer just goes and scans and flushes out of these buffers. But if you, for example, suspend that process or it somehow hangs, the system will continue to function fine. And in many cases, you probably won't even notice. It just means that the backends have to do more work that otherwise the background worker would be doing. The while writer is similar. Its only responsibility is to check if new while records have been generated and flush them to disk. Now, regular backends will do the same thing. If they write and there is no room in the while buffers, they will also flush it to disk. Or whenever you commit, the normal backends will also flush it to disk. So again, this is non-critical. It does the same work as a regular backend will if it has to. But if you're doing like a bulk load, it's better to have a separate process doing the flushing so that the normal backends don't have to wait to do that. So that's just for performance reasons, not very critical processes. Then we have a bunch more. We have the stats collector that is responsible for collecting counter information from backends. Like whenever you run a query, we keep a counter of how many queries have been run and how many transactions have been processed. If you look at the PG stats, PG stat, I forget what it's called, PG stat something, you can see these counters. And it's the one that collects the information for each index and heap, how many index scans have been made. It works kind of, that's kind of special. It's not connected to shared memory. I think it's not. At least it doesn't do much. The way the stats are collected is that the other backends will send a message using it. It will send actually a UDP message to the stats collector that contains new information, and the stats collector will accumulate the messages from all of the backends. So that one doesn't go through shared memory. And the reason for that is that if the stats collector for some reason hangs or doesn't keep up if there's so much activity in your system, the UDP messages the operating system will just start to drop them on the floor. And so the normal backends will never block because they couldn't send the statistics. Because we don't care so much about the statistics. If the system is completely busy, we want the backends to continue working, and we'd rather skip some statistics than stop processing your actual queries. The logging collector is kind of similar. Whenever your backend needs to write something to the logs, do go to the logging collector unless you have disabled that in the configuration file. But I don't think anyone does that nowadays. So whenever one backend needs to put a message to the log, it will send it to the logging collector, which will write the logs. And then we also have while archiving. If you enable while archiving, we will every now and we'll launch the while archiving process, which wakes up every now and then and calls the the archive command. That's the only responsibility of that process. And again, the reason it's a separate process is reliability, because if it's calling any random command you gave it, so we don't want the rest of the system to crash or anything if that command you gave it is broken. So that's why it's a separate process. If that dies, Postmaster will just launch a new one. So that's about processes. I'm going to continue with the shared memory. We have, as I said, backends use shared memory to communicate with each other. It's allocated when you launch the system. It's fixed size. It doesn't grow or shrink after you start it up. And it's divided into a lot of small areas. But like 99% of the shared memory is used for the shared buffers, and that's what you set in your config file. That's like most of the memory actually goes to that. But there is a lot of other stuff, small stuff, in shared memory that the backends use to communicate with each other. And we use something called lightweight locks to protect these areas. So about the buffer pool, it consists of 8 kilobyte pages, and each buffer can hold 1 page. This is pretty, you read on how do you implement buffers in operating systems or databases. This is pretty common stuff. Each buffer can be locked in read or write mode. And these are really low-level buffers. It contains just the exact image of what is on disk. That's chart up there if someone wants to look it up. That's what we store for each buffer in addition to the real data that's in. There's some logs and stuff. But there are other important stuff. Besides the buffers in shared memory, we have what we call a proc array. So every backend process that we launch has a slot in this array we call a proc array. And it records some basic information about that process that other processes need to look at. Like what database is this connected to? What's the process ID? If you do PS and look at the processes in your system, which process is this? And what transaction ID is it working on? And then we have some stuff for participating in logging. Also, this is used when you run queries to see which transactions are running at the moment so that we can get a consistent snapshot. It scans the whole array and collects all the XIDs of what's running at the moment. There's all kinds of random little things in there, like is this process running vacuum at the moment? Sometimes we need to know that. There's small flags like that. Whatever a backend needs to publish about itself, it's usually in the array. And as I mentioned, this is really small. It's like less than 1 kilobyte per connection. It's tiny compared to the share buffers. But it's very important, very central concept in the backend. Other thing is we have the log manager. Whenever you do queries on tables, this is what prevents. So if you have one backend running a query on a table, it locks the table, not in an exclusive way, other processes can access it, but it prevents other backends from dropping the table while you're querying. And that's what we have in the config file called max logs per transactions and max connections. That specifies how much space we reserve for that. Again, it's fixed size, so if you run queries that access thousands of tables in any query, you might run out of space and you get an error message. We have a deadlock detector for that. And then we have a lot of random other stuff in shared memory, like whenever you run the checkpoint command, It's not that process that does the checkpoint. There's a separate checkpointer process, so there's a little bit of memory reserved for communicating with that, and a bunch of other stuff. I'm not going to go through this. But there's a lot of tiny little areas in shared memory for random purposes. And then we have some other caches there, like there's a cache for log buffers, the write-ahead log, C log, and these are all directories you can see in the data directory. Subdirectories there. And they are all handled similarly. They're small buffers, tiny compared to shared buffers, but important for the backend. We have a table of prepared transactions and some miscellaneous stuff. So another area we have in the shared memory is something that we use to communicate with the postmaster. I said earlier that the postmaster doesn't touch shared memory. It's not really true. It does a little bit. So there's a tiny little area that's reserved for communicating with the postmaster, and there is no looking there. It's very simple, just some flags, signals. So we have that in shared memory, and then we have what we call shared cache invalidation for invalidating backend private caches. Yeah, we have a lot of locking there. We have 3 levels of logs. I'm not going to go into details, but we have spin logs that are used to implement lightweight logs. And lightweight logs are what usually protects all of these shared memory areas, but they're also used to implement the heavyweight logs. Anyway, what's important to notice is what we don't have in the shared memory. There is no plan cache, for example, in the shared memory. This surprises a lot of people. If you run a prepared statement in one connection, it's going to run the optimizer and it's going to generate the plan, but that's held within the backend. It's not shared with other backends. Many other databases do it differently. But in Postgres, it's per backend. Other thing we have is what we call a catalog cache. We cache information about operators, functions, tables, indexes, whatever you need to access. Because the shared buffer cache that we talked about earlier, that's very low level. It only contains the raw images of the pages on bits. It's very low level. But these catalog caches, we parse the information a little bit more, and we have internal structures, complicated structures with pointers and stuff like that to have more information on the indexes and what table is it related to and so forth. It's a lot more high level. And obviously workmem is not in shared memory. But this means that the structures we have in shared memory are very simple. It's kind of they have to because it's fixed size, so you can't dynamically allocate memory easily and move things around. But it makes it very difficult to work with sometimes, but it's also a blessing because it forces you to keep things simple in shared memory. And that's important so that if the one backend crashes, it doesn't affect the other backends. Okay. So, kind of the third part I'm going to cover is stuff we have in backend private memory. This is not shared. What we have in backend private memory is, I mentioned, local caches of information on tables and indexes. We have that. Data types, functions, so forth, and yeah, this is the same stuff. But to invalidate these things, we have the thing I mentioned earlier, which is a shared cache invalidation thing. So whenever you drop a function or an operator or a table, what we send, that backend broadcasts a message in shared memory to all the other backends saying, I did something to this table. If you have that table in your private cache, you want to invalidate that because the table might not be there anymore. So whenever something changes in these caches, we send up. Memory is not fixed size. Shared memory is fixed size, but backend private memory is very flexible. We have what we call memory contexts. Memory contexts are hierarchical, so that we have a top memory context that contains everything, and within that we have a per transaction context, and that contains stuff that's important for the transaction. And within that we have a context for query level stuff, and within that for row level stuff. And this makes memory management really easy. When you write backend code, you usually don't need to worry about freeing anything, because it goes into the memory context, and that will be automatically just zapped at the end of whatever you're doing. And it also means that it's pretty easy to actually write C functions extensions in C, in Postgres. We have a lot of infrastructure like memory management that, if you write your own C application from scratch, it's complicated stuff to get right, and you will have memory leaks very easily. But if you do it in Postgres, if you're writing C extensions in Postgres, it's much more like writing Java code or whatever. It's easy to work with. So yeah, you can see that we have this hierarchy. If you ever run out of memory, Postgres will print out this in your log. I hope it never happens to you, but it does sometimes. Sometimes you run out of memory, and we handle that very nicely. So you can see kind of where the memory goes. This one was from a backend that was just running one very small query, so there isn't very much there. But you can see that it's a hierarchy. Another thing we have, which is super nice, we have very nice error handling. We have, whenever something goes wrong in the backend, we just throw an error, and this is exactly like C++ or Java exceptions, really. You throw an error and it never returns to what we're doing. It jumps back to an error handler that will roll back the transaction automatically, release all the logs you were holding, it will release all the memory that you were holding. So again, it's very much like writing Java or C++ code, not plain C code. And that's very nice. And then we have a more serious error. If something goes seriously wrong, you can kill the whole backend. But the rest of the system runs. And then we have panics, which you hopefully will never see. If something goes seriously wrong, then you can panic and bring down the whole server. So, in summary, it's very easy to work on the backend because we have these memory contexts, we have very robust error handling. It's very easy to write C code in the backend. Usually you don't need to worry about shared memory at all if you write your own code, because it will just all run within the backend and all the difficult stuff is there for you. And that makes it really robust when you write your own C extensions. So that's all I have. This could go on forever, it's a broad topic. But it's just some basic stuff I wanted to cover. Questions? Yes?
We have the round workers we can write now. And if I want some trigger to send some information to the ground worker, and in the ground worker to include the case so that's for triggers.
Right. So the question is, if you want to send some information from a trigger, for example, to the background worker, I think you have a few options. You can allocate your own shared memory stuff. I listed all those little things for different purposes. That was kind of the internal stuff, but you can also allocate in your extension. You can allocate your own small fixed size block of shared memory and use that to communicate. Well, it's a bit tricky to send a message, then you have to worry about you have to size it right, and what do you do if it's full and so forth. But I think in 9.4 we have something called dynamic shared memory, which isn't currently used for anything, but you can use it in your extension, and I think we have a queue implementation there. You can actually send message and have someone receive it. It would actually be, if you're really doing that, it would be good to look at that, because I don't think anyone is using it at the moment. So it would be good for someone to use it so that we know if it's any good. So please take a look at that. But you can also send signals, Unix, just signals between processes, if that's all you need to wake someone up. But, yeah.
Hi. For what reasons are you not caching plans? Why are you caching plans only for connection?
Well, it's usually easier just to work in backend private memory, because then you can easily have pointers and it's dynamic, you don't care how large it is. Shared memory is fixed size, so then you run into problems like if you run out of memory, what do you do? So it's just generally much easier to work within the backend than in shared memory. That's the main reason.
But doesn't it affect performance for other connections?
Yes.
That could use the plans more effectively.
Sure. Yeah. It's a trade-off. If it was shared, then when a new backend launches up, it would immediately use the plans. Yes. And it also means that you waste more memory if you have 100 connections and they all have the same plan in their own cache. You lose some, it's wasted memory basically. One connection, run one query and kill it, because that gets expensive. because all of these caches are within backend private memory, that's a big reason why it's so slow to launch a new process. So yeah.
Thank you very much. It was very interesting. I have a question related to process architecture.
Yeah.
As I see, there is not much parallel stuff you can do in Postgres. You may have several vacuum workers, slaves, but you don't have several background writers or a whole recovery process. And
Yeah.
why?
Good question. We should have. No. Like the background writer, it's usually very idle. There is no need to scale it to have multiple ones. Because if it blocks, because that means that you're busy doing the I/O, so it wouldn't help to have multiple processes. Same with the val writer. If that blocks, it means that it's actually flushing stuff to disk, and the disk is way, way slower than how fast you can send stuff to disk. So for those two things, you don't need it. For the startup process, yeah, that is something we will hopefully address at some point. It's true, the val recovery is single-threaded. It's a single process running a single thread. So we could speed that up a lot if we had multiple processes doing it in parallel. It's kind of difficult because there can be dependencies between different val records, so you need some bookkeeping to make it work. But hopefully we'll do that eventually. And it would be doable. It would just have multiple startup processes, and then they would communicate and decide who does what. It's no fundamental reason we couldn't do it, but it's a lot of programming and hasn't been necessary up to this point.
Thank you. And the second question is related to inter-process communication.
Yeah.
You have mentioned lightweight spin locks. It's something like Oracle latches, indexes. Yes.
Yeah. Mutex is, yeah. Not sure what terms.
I mean, does process really spins on the CPU?
Yeah. So the lowest level locks are spin locks, and yeah, you really do spin. It's a busy way to loop. But we use that only to protect like very short, few lines of code, very short segments. And we use those to implement the higher level locks. The lightweight locks are different. We have proper queuing for them, and you sleep, and we have shared and exclusive modes, and they are really handy. We don't have deadlock detection for them, and we don't need to usually only hold a few locks at the same time. Yeah, and then we use those locks to implement the even higher level locks for table lock users. In 9.5, Andres Freund is working on atomic operations, so the lightweight locks will hopefully use those, at least on platforms that support them. Basically make them more scalable. That's what it's all about. And in some cases, you can get rid of the spin lock if you can use an atomic operation, just a single assembler instruction instead. But we'll see where that goes.
But please tell us something more in detail about change plane for 9.4, 9.5.
So it's go on.
About future architecture.
Oh, future architecture.
For 9.4, 9.5.
Yeah, so there has been any big.
Let's do our talk.
Yeah. So what are we going to do in the future? I can't think of much. I think in the future, Robert Haas is working on doing parallel query. That will, for example, if it's the same architecture, we're just going to have more processes that are like worker processes, and they will communicate through shared memory with the backend processes. It doesn't really change the overall, big picture. It stays the same. I can't think of any big architectural changes coming up. That's usually a good sign that the architecture is good if you don't need to change it often. More questions? If not, thank you. And I'm going to be here around for a few more hours.